Hello everyone, this is my geometry channel lesson 5. In the last lesson we talked about congruence and triangles. So it was sort of divided into two parts. This one's similar, it's talking about similarity and transformations. This is also sort of divided into two parts. First we'll be talking about similarity, which is sort of similar to congruence, haha, and then we'll be talking about transformations, which is sort of an application of congruence and similarity. So before we get into similarity, a bit of algebra background. You might know this stuff from Algebra 1, but if not, this is just a recap. So first, a ratio. A ratio is basically a comparison of two quantities, and it's basically division. So I'll give you a quick example. If you have 4 blue balls, and then for white balls, then the ratio of blue balls to white balls would be 4 to 4. The 2 is a colon, or you can also write it as divided by 4 divided by 4. And now we'll get into something important. As you can see by the last notation, this is basically 4 divided by 4. And as with fractions, you can simplify them. This is basically 1. And 1 you can write as 1 divided by 1. So this is equivalent to 1 to 1. So yeah, you can convert to fractions and then simplify and then convert back to ratios, or you can just use the greatest common factor and factor them out, as you do with fractions. Let me try to show you another example, except this time it's a bit more complicated. Only a bit. So this time it's 4 to 3. Just ignore everything on the bottom. This is a new example, 4 to 3. And this you cannot simplify, but you can write it as a fraction, 4 divided by 3. The simplest form, like I said, the greatest common factor has to be 1, which means you can't factor everything up. Equivalent ratios, meaning the simplest form is equivalent. So 4 to 4 and 1 to 1 from our last example, they're equivalent because the simplest form of this is 1 to 1. It's also equivalent to 2 to 2 because the simplest form of this is 1 to 1. And sorry if you can't see the colons in the middle. Anyway, our next topic, subtopic, is proportions. Proportions is an equation that sets two ratios equal. So first we talked about ratios, now we're talking about proportions, and this is slowly going to build into similarity. An example of a proportion is 4 to 4 is equal to 1 to 1. Yes, I'm using that same example. Here we know these two are equivalent, so this is just verifying if it's true or false. But in algebra, you might be able to sort of manipulate ratios in a way that you do with fractions. So what if I said, hey, I have X blue balls and 4 white balls, and I know it's equivalent to 1 to 1. So if I have X to 4 is equal to 1 to 1. So I want to find out X. Well, this is pretty obvious. You see the answer right up here. So X is equal to 4. But let's ponder on this a moment. So you can write it as a different way. X divided by 4 is equal to 1 divided by 1, which is just 1. And as we do with fractions, maybe you remember from algebra, this is basically equivalent to X is equal to 4. You just multiply 4 on both sides. This was easy. I'll give you a harder example. For example, if I have X green balls and 20 yellow balls, and let's say this is the same ratio as 9 blue balls to 12 white balls. Okay, so just saying the color of the balls doesn't matter, which is why I didn't write it down here. It's just this equation that we're given. And yes, it's an equation. It's a proportion. So first, X divided by 20 is equal to 9 divided by 12. 9 divided by 12, we can simplify into 3 divided by 4. So now, as we do with fractions, we multiply both sides by 20. And here, we see that if we multiply by 20, this will also be a whole number. So win-win. we clear both the fractions. So if we multiply by 20, it might take some time, but eventually you'll see that x is equal to 15. So this is our answer for this proportion. And yes, it was a bit harder, but these are mostly the kind of proportions you'll see in geometry, especially similarity. There's different terms in proportions. You've probably not heard of these before, but let's say I have a proportion a to b is equal to c to d. And this can be written as a divided by b is equal to c divided by d. Now, the means are the inner values. Now, what I mean by inner values is basically b and c. On the other hand, the extremes are the outer values, a and d. I'm not going to circle them to distinguish them, but the extremes are outer, means are inner. Think mean as in the middle. I know that the median is actually the middle of a set. Maybe you know this from set theory and maybe even algebra 1, but the mean is usually in the middle. It's sort of like between the two, the lowest and the highest. The lowest and the highest we call extremes, exactly. So which is why A and D are called extremes because they're outer. B and C are called means because they're inner. I'm going to clear this out really quickly. Now, why we introduce means and extremes? Well, there's an important property that you probably know, cross product property. The product of extremes is equal to the product of means. You've probably not seen it in this format, but you've probably seen this. If you have this, that means that BC is equal to AD. This times this is equal to A times D. The mean times the mean is equal to extreme times extreme. And this is from Algebra 1. Yes, it's a review. And we can use this in our previous example. We had x divided by 20 is equal to 9 divided by 12, and we simplified this to 3 over 4. So let's just get rid of the middleman over here. X divided by 20 is equal to 3 divided by 4. Cross product property, 4x, I'm writing on the left-hand side right now because I don't have space here. 4x is equal to 60, x is equal to 15. We got the same answer, and basically it's the same way, except the cross product property is a bit easier as we consider, because we don't have to simplify this fraction by multiplying it by 20. Instead, we just have to multiply 20 by 3, not 20 by 3/4. It's the same thing in the end, except people think that the cross product property is usually easier. And I agree with them. Now, the geometric mean. So yes, you see this equation, x squared is equal to AB, and you think, what in the world does that have to do with ratios and proportions? And this is what I mean. You've probably heard of the arithmetic mean, and it's saying that x, the arithmetic mean of two values, a and b, is a plus b divided by 2. And how do we get that? Well, it's a bit complicated, but it has to do with arithmetic sequences. If I have two values, or more like 3 values, the sum of these 2 values divided by 2 is this value. So yes, that's the arithmetic mean of 2 numbers. The geometric mean is similar, and you can't see it by this, but what if I do this? It doesn't look like it, but it's the same exact equation. You just take the square root of both sides. X equal to square root of AB. This might look familiar to some of you, but if you're still in the dark, let me explain. If I have a geometric sequence, and it's completely fine if you don't know this, we'll be covering this in our pre-calculus and Algebra 2 series in one of the later lessons, of course. But first, let me sort of give you a background. In an arithmetic series or sequence, the values increase by a certain amount. So let's just say it was +2, just for this example. It might not be +2, but so let's say 1, 3, 5. The difference between every pair of consecutive elements, as what they're called, is the same. So 3 minus 1 is 2, 5 minus 3 is 2. If I wrote another one, 7 minus 5 is 2, 9 minus 7 is 2. Keyword consecutive, because 9 minus 1 is not 2, it's 8. Geometric series, as you might guess, by the mean value, it's multiplied by a constant amount. So in this case, we'll look at 2. So let's say we have 1 multiplied by 2, 2, multiplied by 2, 4, and then maybe 8, and then maybe 16, and then maybe 32, and so on. And we can find well, we can verify it, first of all, if it's a geometric sequence by dividing. So 2 divided by 1 is 2, yes. 4 divided by 2 is 2, yes. 8 divided by 4 is 2. 16 divided by 8 is 2. 32 divided by 16 is 2. The ratio is always the same. And here's the word ratio. Ratio basically means division. The ratio is always the same. And this case, it's 2. So the geometric mean of two numbers A and B. So arithmetic, it was x is equal to a plus b over 2. And you've probably heard this term. Maybe you haven't heard it as arithmetic mean, but you've probably heard it as average, or maybe even mean in general, because arithmetic mean is the most common type of mean. This is the geometric mean. And how do you find x? If over here it's easy, because you can use the formulas given through arithmetic sequences. I'm not going to run through them today because that's another lesson in algebra 2 and pre-calculus. I'm not going to run through geometric sequence formulas either, but I'll just tell you x is equal to root AB. And that's the geometric mean. You might still be confused why it's talking about ratios, so I'll explain. What if I had a ratio x divided by, a divided by x is equal to x divided by b. And this is a common ratio we see in geometry, especially in similarity. And cross product property, x squared is equal to ab. Wait a minute, that looks familiar. Yes, it's the geometric mean formula. So this is a proportion, and each of these are ratios, which is what the geometric mean has to do with ratios. I'll explain in a bit about how to get this equation. How do we know that it has to be this? But now we'll be talking about some other properties of proportions. The reciprocal property, if two ratios are equal, then the reciprocals are also equal. So if I have 2 to 3 is equal to 4 to 6, that means 3 to 2 is equal to 6 to 4. Easy. And from now on, you'll probably see me using division notation for ratios. It's just easier. Okay, if the means of two ratios are interchanged, then the new proportion is still true. 2 to 3 is equal to 4, 6. Means we know. Means are 3 and 4. So which means that 2 divided by 4 is equal to 3 divided by 6. Let me try that again. 2 divided by 4 is equal to 3 divided by 6, and voila, it works. And if the denominator on each side of a proportion is added to the numerator, then the new proportion is true. Yes, the words of that sound complicated, but let me just explain. 2 divided by 3 is equal to 4 divided by 6, our handy example. 2 plus 3, you add the denominator to the numerator, divided by 3 is equal to 4 plus 6 divided by 6. And is this true? Well, if you calculate it, let me write up here, actually. 5 divided by 3 is equal to 10 divided by 6. It works. And I'll actually prove this one because most people see it and they think, how in the world do you know that? And this is how. It's pretty simple. A divided by B is equal to C divided by D. We're given that. We're supposed to add, so these are given, and in the bottom I'll write the proof. A plus B divided by B is equal to C plus D divided by D. And what you know, or what you should know about fractions, I'll just run through it really quick. You can split them up. So A divided by B, so A plus B divided by B is equal to A divided by B plus B divided by B. And this is equal to C divided by D plus D divided by D. This is just 1. This is just 1. And voila, you get, if you cancel off 1 on both sides, you get A divided by B is equal to C divided by D. Hence the proof. A scale is a ratio that describes how dimensions are related. And this is more the geometry aspect. So if I have a map, that's probably the most common way of a scale. A scale, let's say I have 2 inches on the map. And this corresponds to 10 miles in real life. That means that the scale is 10 miles to 2 inches. So if I had 20 miles in real life, then it'll be 4 inches. If I had 5 miles in real life, it'll be 1 inch. So yes, a scale is important. A scale drawing uses a scale to make an object easier to see. Scale drawing is 2D, scale model is usually 3D. An example of 3D is probably like a figure of the sun, for example. It's proportional, most likely, to the real sun. And I mostly mentioned that to tell you about a new word, proportional. Proportional means that basically that the ratios are equal. And you've probably heard it before. You might say that, let me just use that same example. The model of the sun is proportional to the real sun. You might just say that without knowing what it means. But it basically means that the ratios of the dimensions of the model is equal to the ratio of the dimensions of the actual sun. And that's what it means by proportional. Okay, finally, we get into some geometry, actual geometry. So similarity. Similar polygons are when corresponding angles are congruent and corresponding sides are proportional. Congruent, remember, congruent polygons had corresponding angles as congruent and corresponding sides as congruent. This corresponding angles are still congruent, but corresponding sides are proportional. Here's that word again. It basically means that the ratio of one side to another side on the same figure is equal to the ratio of this corresponding side to the corresponding side on another figure. Similarity statements, they show similarity, and it's basically like a congruent statement, except there's a new symbol. Congruence was this, similarity is this. So you say figure A is congruent to figure B. Triangle ABC is congruent to triangle DEF, and so on. Scale factor. So we talked about scale. Now the scale factor, it's also called a similitude, and it's the ratio of lengths of corresponding sides. So if I had, let's just go with triangles because triangles are easy. Two similar triangles, and let's say this was length 2, this was length 3. And let's say I knew they were similar. Then the similitude or the scale factor of these two triangles, let's consider this one over this one. It'll be 3 over 2 or 3 to 2. Corresponding lengths in similar polygons. This is sort of a theorem, property, whatever you want to call it. If two polygons are similar, then the ratio of any two corresponding lengths is equal to the scale factor. This is basically the definition of scale factor. Now, here is something interesting, actually. The perimeters of similar triangles are actually, they're not the same, but they're proportional. And the ratio of the perimeters is equal to the scale factor. You might be wondering why. Let's say I have A, B, and C, just to generalize it. I know this is only for triangles, but you can prove it on any figure you want. And this is A1, B1, C1. Yeah, I know, I'm creative. So the scale factor is equal to A1 over B1, which is equal to, A1 over A, which is equal to B1 over B, which is equal to C1 over C. Now the perimeter, I'll write on the top. The perimeters of them would be A1 plus B1 plus C1, and the perimeter of the bottom would be A plus B plus C. And it looks complicated at first, but you can use some of the theorems we learned, including the property that you have to, if you add a denominator to the numerator, there's actually a slight variation of that. You could add, let's see, so it's hard to prove right now with the concepts we learned so far, but it's important to note that the perimeters of similar triangles are proportional. And I can show you this with an example rather than a proof. Let's say it was 2, 2, and 2, just for simplicity's sake, 3, 3, and 3. Then this perimeter of this would be 9. The perimeter of this would be 6, which is 3 to 2, which is the similitude. So in triangles, we're going to focus on triangles now. And AA, you might recall this from our previous lesson. And yes, these are similar to the congruency theorems. Similarity theorems, so AA means that two angles are congruent. SAS, two sides are proportional, not congruent, proportional, and the included angles are congruent. SSS, three sides are proportional. You might notice that I'm running through this pretty fast, and this is because if you haven't already watched the previous video, you probably should, because congruence lays a base for similarity and transformations. Yeah, so just pause this video and go watch it if you haven't. But if you have, you'll probably recall that A is angle, S is side. So you can probably draw examples on your own. It'll take too long to draw examples over here. And it's easy to see once you've learned congruence. Some other theorems. So these are the three main similarity proving theorems, but there are some other theorems too. The triangle proportionality theorem, if a line parallel to one side of the triangle intersects the other two sides, then it divides the two sides proportionally. Triangle, it's parallel to the other side, the third side, and it intersects these two. That means that if this is A, this is B, this is C, this is D, A to B is equal to C to D. And yes, it's a pretty complicated proof. Parallel transversals theorem, if three parallel lines intersect at two transversals, then they divide the transversals proportionally. So let's add these two transversals here, A, B, C, D. That means A divided by B is equal to C divided by D. And yes, I know in this picture, I made it look like the two transversals were parallel. So let me draw a better picture to indicate that that doesn't have to be true. This and this, why not? That means if this is A, B, C, and D, A divided by B is equal to C divided by D. Angle bisector proportionality theorem. So the angle bisector of a triangle, it divides the opposite side into segments, and these lengths are proportional to the other two sides. That's a simple way of putting it. So let's say I have this triangle. This is the angle bisector. This is A, this is B, this is C, this is D. A divided by C is equal to B divided by D. You can also write it as we're used to. A divided by B is equal to C divided by D. Oops, C divided by D. Okay, now we're going to the second part, transformations. A transformation is an operation that moves or changes the geometric figure to produce a new figure. That's the complicated version. The simple version, you're basically turning one figure into another. The preimage is the original and the image is the transformed. There are different notations. The mapping notation, you're basically saying that a transformation T, we usually use T. Can you guess why? Yes, because transformation begins with T. So T maps, and this is usually indicated by an arrow, figure A to figure B. So you might say T maps, or T, what it does is it maps A to B. That's not that common. More common is prime notation. You say A to A prime. There's also coordinate notation. You almost always use the 2 as the arrow. Coordinate notation, x comma y goes to t of x comma t of y. And this looks complicated, but it's just saying the new coordinates. An isometry is a transformation that preserves length and angle measure. These are basically congruence transformations. Can you guess why? It's because a congruent figure has the same length, basically it preserves length, and the same angle measures. It preserves angle measure. It's also called a rigid transformation. Don't ask me why. A non-rigid transformation, on the other hand, doesn't preserve length or angle measure. So we're going to split up into different types of transformations. The first one is a translation, and this moves the figure. So it's basically sort of like pushing it. And the stuff about every point in the same distance and the same direction. It's basically saying you move this much, you move this much, you move this much, same distance, same direction. And you get this new figure. This is an isometry, by the way. So the general formula, if you move it A units horizontally and B units vertically, the coordinates of the point XY on the figure become X plus A, comma Y plus B. And this is pretty obvious for those of you who studied functions already. If you recall, in functions, if you move a function horizontally, you do a plus A or minus A, depending on if it was right or left. Right is minus A, left is plus A. And moving it up, it's plus B or minus B, depending on if it was plus or minus. Usually use H and K, not A and B, but it results in the same thing. Now, if you go back to my old picture, you might notice that I used arrows, and this on purpose. This is because of vectors. And vectors have both direction and magnitude. It's basically a quantity that has both direction and magnitude. That's confusing, yes. But think about the number 2. This is called a scalar because all it has is a magnitude. Magnitude is basically like a size. This is size 2, basically. A vector has a direction and a magnitude. So it has the direction. So let's just take this one, for example. It's a direction this way, and its magnitude is its length. So it's like 2. Bit about vectors. The initial point is the starting point of the vector, and this is the pre-image. And this is called the terminal point. The horizontal component is the change in X, and the vertical component is the change in Y. I use delta X. For those of you who are familiar with slope, delta X means change in X, delta Y means change in Y. The component form uses horizontal and vertical components. So A comma B, where A is the horizontal, B is the vertical. Reflection. So reflection uses a line of reflection to reflect the figure. You know, in English class where your teacher never tells you to never use the definition, to never use the word in its definition, we're basically breaking that law 100 times. First of all, what's the line of reflection? And to reflect a figure, what does reflect mean? Yes, I know this is a bad definition, but it's basically the simplest definition. Unless you want a figure, that would be easier to explain. I know that doesn't explain much, but at least it tells us what a line of reflection is. It's the line in which you reflect by. We're good at this. It's also an isometry. Here's some important formulas or rules. When you do it across the x-axis, the point xy becomes x negative y. You can prove it. I'm just going to show you a picture and it'll click. If this is x comma y, reflection, basically, you move the same, let's say the distance between the point and the line of reflection is d. You move d from the line of reflection to the opposite side. And this has to be perpendicular to the line of reflection. I know it looks confusing, but if I have this point, what you would do is measure this and do the same thing here and make sure this is perpendicular. So yes, as you can see in this beautiful diagram, this point will have x comma negative y because you're moving y down and y down again. So if y down gives it a y value of 0 while its x value is the same. Another y down, x value is the same, y is negative y. Across y-axis becomes negative x comma y in a similar manner. Across the line y is equal to x. So x comma y becomes y comma x. And for those of you who studied functions, this is basically the definition of an inverse function. You basically reflect across the line y is equal to x, and you basically switch x and y. It seems easy at first, but when you talk about functions and inverse functions, it's not that easy. So across the line y is equal to negative x, it's negative y comma negative x, as expected. Across the line x equal to a, so not the x-axis, but a horizontal line. Sorry, a vertical line. This is basically a translation of the y-axis. And this becomes 2a minus x comma y. You probably want to write this down because these formulas are really helpful. When your geometry teacher gives you reflection problems, they're not going to be simple x-axis or y-axis. They might, but most of the time it's going to be something complex. And I'll get to the complex ones in a minute. Across y is equal to b, it's x comma 2b minus y. And across the line y is equal to mx plus b, this one might be a cruel problem your teacher gives you. And I suggest you look it up because this is way too hard to write down. If you do want to learn more, your teacher might not give you this problem, but maybe as an extra credit, he or she might give you this problem. Across the line y is equal to 2x plus 3 maybe. And if you don't know what to do, then let's face it, you're stuck. So it's helpful to find out this formula. There are a lot of places you can find out this formula, or you can try proving it yourself. And similarly, in standard form of an equation, ax plus by is equal to c, again, search it up. You might want to take notes on this. Rotations. So rotation is a figure that is turned around the center of rotation by a given angle. Again, what's the center of rotation? It's the center at which you rotate by. And the angle you're given is the angle of rotation. It's an isometry. And here's a big note. Angles are usually counterclockwise. Negative angles are clockwise. So 90 degrees would be 90 degrees counterclockwise, this direction. And I know that's not familiar because clocks always run clockwise and you're expected to do clockwise, but math is just about disobeying rules. Speaking of rules, 90 degrees around origin, it's negative y comma x. 180 degrees, negative x comma negative y. 270 degrees, y comma negative x. I suggest you take notes on this. It's hard to remember, unlike the reflections. And now we'll be talking about around points, centers of rotations that aren't the origin. So around y comma b, sorry, a comma b, it'll be a plus b minus y comma x minus a plus b. Yes, it's as complicated as it looks. 180 degrees, this is the same as doing a reflection over both the y-axis and the x-axis, and this will give you 2a minus x, 2b minus y. 270 degrees around a comma b, it'll be y plus a minus b comma a plus b minus x. 360 degrees is just xy becomes xy, no matter where you rotate around. Now, what about one of these, not one of these nice angles, r degrees around the origin? For that, you'll need trigonometry, which is why I didn't give you the formula. But if you're familiar with trigonometry and you think you'll be able to do it, I suggest you to look it up and take it down in your notes. It involves cosine and sine. Similarly, r degrees around AB, this is even more complicated, of course. So some more stuff about transformations. A composition of transformations is when two or more transformations are combined. So an example is, let's say I have this point. I want to reflect it across this first, and then I want to rotate it 90 degrees clockwise. So it'll be negative 90 degrees, if you recall. So this is basically a composition of transformations. Composition of isometries is an isometry. There are certain types of compositions that are commutative, meaning the order doesn't matter. You may recall the commutative property of addition, of multiplication, and that's basically saying order doesn't matter. Not all compositions are commutative, but I'll give you an example of some that are. Glide reflection, for example, is reflection and translation parallel to line of reflection. So if this is the line of reflection, you first reflect, and then you translate in the same direction as the line of reflection. This is commutative. Reflections over parallel lines, also commutative. first and then reflect again. Reflection over intersecting lines. Now this one isn't commutative, and in some cases the previous one isn't commutative either. But the reason I mentioned these is because you can actually, instead of doing this exact thing, you can sort of make it easier. So for over parallel lines, you would do a translation twice the distance between parallel lines. So not always is this commutative. Sometimes it is. But if this is the distance d, that means you basically translate this point 2d. Similarly, if this is the angle, we normally use theta for angles. The rotation, it's basically a rotation twice the angle, 2 theta. Now symmetry. Symmetry has to do with transformations. Line symmetry is basically reflection. So a square, for example, has lots of line symmetry. Literally 4 lines. A rectangle, on the other hand, only has 2. If you reflect the figure over that line, then it's still the same figure. The line of symmetry is the line of reflection. On the other hand, rotational symmetry, it can be mapped onto itself through a rotation. Square, for example, if you rotate 90 degrees, you get the same. 180, same. 270, same. And 360, same. The angle of symmetry is the smallest angle of rotation. The center of symmetry is the center of the figure, and a point rotation is 180 degrees rotational symmetry. A figure with point that does a point rotation has point symmetry. And if you flip a rectangle 180 degrees, you get the same figure. Non-rigid transformations. We briefly mentioned this in the beginning, but here's some more details. Famous one, dilation. And this has to do with similarity. So go back to the first few minutes of this video in case you want to. The scale factor K is the ratio of side length of the image to the side length of the pre-image. Enlargement is when the K is greater than 1, and reduction is when K is less than 1 but greater than 0. So I have this triangle and I have this triangle, it's an enlargement. If I have this triangle and this triangle, it's a reduction. Some of the formulas, if it's centered at the origin, xy becomes kx, ky. If it's centered at AB, it's kx minus ka plus a, comma, ky minus kb plus b. Some other non-rigid transformations are shrinks and stretches. Horizontal shrink or stretch is when you just change the x value. xy becomes ax comma y. If a is greater than 1, stretch. A is less than 1 but greater than 0, shrink. Similarly, vertical, it's x comma by. B is greater than 1, stretch. 0 is less than b, which is less than 1, shrink. And that's it for today. Today we talked about similarity and transformations. In the previous one, we talked about triangles and congruence. So these 4 were basically key lessons in geometry. These 4 topics, but the past 2 lessons, of course. The next lesson will be right triangles, trigonometry, and quadrilaterals. A bit advanced, but it would be necessary, especially trigonometry. You won't survive half of algebra 2 without trigonometry. So on that happy note, see you next time.